Hi everybody and welcome to session 5 of Phil 2002 Logic, How to Defeat Your Foes with Reasoning. In the last couple of sessions, what I've done is introduced you to a basic language for translating out argument. And what we've got with respect to this basic language, which we call propositional logic, is a syntax and a semantics. And remember that the goal of developing this language is to come up with a foolproof method for working out whether or not an argument is good or bad, where that pertains to validity. And recall the concept of validity: an argument is valid when it's impossible for the premises to be true and the conclusion false. And so what we're going to do is we're going to try and use this basic language in order to understand validity. That's where we're aiming for. What we did in the last session was look at joint truth tables. So remember that a truth table provides the semantics for the language, helps you to understand it, and then you can also use truth tables to classify different propositions. And so what we were doing is we were taking propositions, putting them into joint truth tables, and then trying to say something interesting about the relationships between them. What we're going to be doing today is taking that a step further. So we're now going to produce joint truth tables in which we situate entire arguments. And once we situate an entire argument inside a truth table, what we can actually do is prove that the argument is valid or invalid. And where by proof, I mean something like the mathematical sense of proof. The results that we get will be absolutely precise and completely true. You won't be able to deny that these arguments are valid or invalid using this kind of method. Before we get there, let's just recall our understanding of the syntax and the semantics of propositional logic. So remember, the syntax of propositional logic has these propositional letters, A, B, C, D, and so on. Those propositional letters are used to represent entire propositions. Those are things that can be true or false. And in particular, those propositional letters are used to represent basic propositions, propositions that don't have any other propositions as parts. In addition to the basic propositional letters A, B, C, and D, what we also have are the connectives or, and, not, if, then, and the biconditional. So the or connective is the disjunction, either A or B are true. The wedge is the conjunction, the and, A and B are true. The angle bracket is the negation, that says it's not the case that something is true. The arrow, if then, the biconditional, when two things stand or fall together, and then the brackets in order to eliminate ambiguities. And following on from the syntax, we have the semantics of the language. And the semantics of propositional logic gives us the conditions under which each of the propositions, the complex propositions, where we take a basic proposition and add some connective to it, either negation to it or an and, an or, an if then, whatever. We take one of those and we actually give an understanding of the meaning of that proposition, the conditions under which it's true and false, as a function of the basic propositions that feed into that connective. And remember, we drew this box, this machine, that takes in our propositional connectives and then spits out some value for the truth or falsity of the entire complex proposition. So for the negation box, what that does is it takes in a basic proposition, and then the negated proposition has the reverse truth value of the basic proposition. The conjunction, well, that's taking in two propositions, and that's only true when both of the propositions that feed into it are true, and it's false in all the other possible situations. The disjunction, that proposition is true for all of the values of A and B that feed into it, except for the case in which A and B are false, in which case the disjunction turns out to be false. For the conditional, when we have the first thing, so we've got the thing on the left-hand side of the conditional, but we don't have the thing on the right-hand side of the conditional, we don't have the second thing, then the conditional is false, which is this second situation when A is true and B is false, then A arrow B is false, but it's true in all the other situations. And for the biconditional is true when the two sides of the biconditional are standing or falling together. So when both sides are true, then the biconditional is true, and when both sides are false, then the biconditional is true, and it's false in all the other situations. All right, so that's the syntax and the semantics, just to remind you of the language. And remember, what we could do is we could take complex propositions in our language, situate them inside these joint truth tables, and then evaluate the two propositions in order to get some value for both propositions and then to compare them. So remember, we had things like logical equivalence when the two propositions had all of the same values for their truth tables. We had contradictories where the two propositions have different truth values for every row, and so on and so forth. What we're going to do is we're going to now take these joint truth tables and we're going to use them to understand validity. So let's think a little bit about what we're doing here. So what we're doing is we're actually now going to use these truth tables, which up until now we've used to provide the semantics for the language in order to analyze certain propositions. We're actually going to use these truth tables as a proof system. And so what that means is that by situating certain things inside our truth tables, those truth tables are actually going to give us information about the relationships between premises and conclusion, and that information will have the status of a truth, and status of a proof. And in particular, what we'll be able to do is prove that an argument is valid when it is, or invalid when it is. We're also going to take that a little bit further. We're going to look at some fairly general results that you can draw out of the truth table system. But for now, and for this session, I'm just going to focus on showing you how to take an argument, situate it inside a truth table, and then prove that the argument is either valid or invalid. Now remember, validity is a function of possibility. When an argument is valid, it's impossible for the premises to be true and the conclusion false. And remember, our truth tables are also maps of possibilities. On that left-hand side, the start of the truth table, we have all of the possible combinations for the basic propositions that you're feeding into the truth table. And so the truth table system is sort of tailor-made to represent a map of the possibilities, and it's the map of the possibilities that we need in order to determine results for validity and invalidity. So the truth table system is really built to provide us with what we need when we're thinking about valid and invalid arguments. Okay, so let's have a look at a particular argument. What we're going to do is we're going to prove that the argument is valid using our truth table system. Now, remember that when we prove that an argument is valid, all we're doing is proving that it passes one test for being a good argument. Remember, there are two tests for an argument to pass to be a good argument. It has to be valid, right? That's the first test that it passes. And then for it to be a good argument, it has to be sound as well. So validity is just means that if the premises are true, then the conclusion has to be true, but it doesn't tell you anything about whether or not the premises are in fact true. And then soundness is validity plus the fact that the premises have to be true. We're just focusing on validity, though I'll have a little bit to say about soundness as we go ahead. All right, so consider this argument, which I've got up on the slide for you. If the moon is made of green cheese, then God exists. The moon is made of green cheese, so God exists. So what we're going to do is we're going to take this argument. First of all, we're going to translate it into our basic propositional logic. And we're going to, in so doing, we want to translate out each of the premises, get their logical form, and then we're going to situate that entire argument inside a truth table. We're going to complete the truth table, and that will provide us with our proof. Okay, so let's start by drawing up the argument. So we've got two basic propositions here. We've got A, We've got A, which is that the moon is made of green cheese. That's what we're going to say A is. Okay, so that's our first basic proposition. Our second basic proposition is that God exists. Okay, and now the structure of the argument that we're interested in is just this. If the moon is made of green cheese, then God exists. That's our first premise. The moon is made of green cheese. That's our second premise. Conclusion, God exists. Okay, so that's our basic argument. So I've just taken the argument, translated the basic propositions out into the logical, the propositional letters, and then I've been able to derive the logical form of the argument. So this is the thing that we're trying to test. What we want to know is this a valid argument? And in order to work that out, what we do is we situate the whole thing inside a joint truth table. So let me show you what that looks like. So first of all, we're going to build our truth table. And remember, our truth table, we start with our matrix on the left-hand side. And in putting that matrix, we've got two basic propositions. We've got A and B. That's what we're putting into our argument. So we're just going to have 4 lines in the truth table. Remember, the number of lines in the truth table is 2 to the power of n, where n is the number of basic propositions that you have in your argument. So we've got 2 basic propositions, which gives us 4 lines. And when we're setting this up, in order to get out all of the combinations, we just start from the first proposition here. We go T, F, T, F. and then for the second proposition, TTFF. And that's going to ensure that we get all 4 distinct combinations mapped into the truth table. If you had 3 basic propositions there, if you had A, B, and C, you'd start with C, you'd go T, F, T, F, T, F, T, F, which would give you 8 lines, and then B would be T, T, F, F, T, T, F, F, which is another 8 lines, and then A would be T, 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 F, 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 which would be the final 8 lines, and that would give you all of the possible combinations for those 3 basic propositions. We've just got 2 basic propositions though, so that's what we're going to focus on. Now we're going to put each of our premises into the argument. So the first premise was if A, then B. Our second premise was A, and then we put our conclusion in B. Now what I like to do in order to just make it super clear which bit's the conclusion is just put in a little therefore symbol above the conclusion, just so you keep track of which thing's the conclusion, which thing's the premise inside your argument. All right, now what we do is we just complete a joint truth table for the argument, starting with the first premise. Now, first premise is A, arrow B. Now, remember the truth table for the arrow tells us that it's only false in one situation, and that situation is when you've got the first thing and you don't have the second thing. So we're going to put that situation in first. We know that that's an F there, and then it's T for all of the other possible situations. Now for A and B, putting in the truth tables for those is straightforward. We've already got that information over here. So we're just going to replicate that information inside our premises and our conclusions. So we're going to start with A, that's just TTFF, because it's the same as this one over here. And then we do B, which is TFTF. All right. And that's the end. That's the final truth table for this argument. Now what we need to do is we need to try and work out the sense in which this is a proof of the argument and whether and try and determine what it's telling us, whether it's telling us that the argument's valid or invalid. In order to work that out, we have to think once again about the definition of validity. Remember, an argument is valid when it's impossible for the premises to be true and the conclusion false. What we've got here are all of the different possibilities for the premises, all of the different possibilities for the conclusion. This is the entire mapped possibility space for this argument. So in order to work out whether the argument is valid or invalid, we can read that directly off the truth table. When we're looking for a valid argument, what we are looking for is for there to be no row in which the premises are both true and the conclusion is false. When the argument is invalid, there's some row in which the premises are true and the conclusion's false. So we're going to look at the argument row by row, starting with the first row. If we start at the first row, we look to see whether the premises are true. Yes, the premises are both true together. Is the conclusion true? Yes, the conclusion's true. So that's not a row that is going to trouble us, right? It doesn't. The argument, for all we know, is not invalid yet. We look at the second row. The first premise is false, so that's not a row in which the premises are true and the conclusion false. We look at the third row. The first premise is true, but the second premise is false, so that's not a row in which the premises are true and the conclusion's false. We look at the fourth row. The first premise is true, but the second premise is false, so that's not a row in which the premises are true and the conclusion's false either. So we've looked at all of the possibilities, all of the possible situations for the premises and the conclusion, and what we can see is that for each of these, which is each of the possibilities, there is no possibility in which the premises are true and the conclusion false, and because there's no possibility in which the premises are true and the conclusion's false, we know that the argument is in fact valid. And this is a proof of that result. There is no doubt, looking at this, that on the one hand we've mapped all of the different possibilities, and on the other hand we've worked out whether for each possibility in which the premises are true, the conclusion's also true. Since for whenever the premises are true together, the conclusion is also true, we've got a result where the argument is in fact valid. All right, let's take a look at another one. So this is the first one. So this argument here we've just shown turns out to be valid. Now it's very important to recall what I said a few moments ago, that this is one test for whether or not this is a good argument. It doesn't demonstrate that the argument is good overall, because in order to show that the argument is good overall, it has to pass the second test, which means that it has to be sound as well. But the argument is of course not sound, and that's because at least this second premise is false, because the moon is not made of green cheese, if not this first premise. The moon's being made of green cheese has nothing to do with the existence of God or not, so we wouldn't expect that first premise to be true. So both of the premises are probably false here, and because of that the argument isn't sound, but it is valid. If the premises were true, then the conclusion would be true as well. Okay, so let's have a look at this second example. If I'm cooking, then I'm not cleaning. I am cleaning, therefore I'm not cooking. So we're going to do exactly the same thing. We're going to start by translating the argument out into its logical form. We take each of the basic propositions, we assign them a propositional letter, and then from there we work out the logical structure. Our ands, our ors, our if-thens, our nots, we put those in, and once we've mapped that logical structure, we situate the entire thing inside a truth table, we complete the truth table, and then we look to see if there is any row in which the premises are true and the conclusions false. If there is some row in which the premises are true and the conclusions false, then the argument is invalid. If there is no row inside the entire truth table, then in which the premises are true and the conclusions false, then the argument is valid. All right, so let's get going. So we're going to start by doing the translation. So we're translating out our basic propositions. The basic propositions here are I am cooking. That's our first basic proposition. And then our second basic proposition is I am cleaning. And now the structure, the logical structure of the argument, or the form of the argument, is this: if I am cooking, then I am not cleaning. I am cleaning, therefore I am not cooking. Okay, that's the logical structure of the argument. Here's my first premise. Here's my second premise, and then here's the conclusion. So what we're going to do is we're going to take that entire argument, we're going to situate it inside a truth table, and we're going to conduct another proof. So let's take that step. So again, we start by mapping out our possibilities. We've got two basic propositions, so we're going to have the same number of possibilities, which is to say we're just going to have 4 lines in our truth table. We start over here with T, F, T, F for B to get the 4 possibilities for that, and then for A, T, T, F, F, and that gets us all 4 of our possibilities. Now once we've got that, we put in all of the premises and the conclusion of the argument into the joint truth table. So we're going to start with our first premise: if A, then not B. We're going to move on to our second premise, which is B, and then our conclusion, not A. All right? And now once we've done that, we're going to evaluate the truth table. First, I'm going to do what I did before, which is just mark up the fact that that is the conclusion, just so I can keep track of which part of the argument is the conclusion, and so I know where to look to see when I'm trying to work out whether the premises are true and the conclusion's false in some row. Okay, remember in the first session I gave you on truth tables, I said do your negations first. That's what we're going to do here. So we're going to do the not B first, and that's going to be just reversing the truth values for B. Okay, and then we're going to do not A, and that's going to reverse the truth values for A. And now we can put in B as well, because that's easy. We've done now more than half of the truth table just by putting in that information. What we have to do last is this arrow. First of all, we're going to put in A again. And now what we're doing is we're evaluating this arrow using the semantics for the arrow based on the values for A and not B. Again, what we look to see is if there's some situation in which you've got the first thing and you don't have the second thing. If there's one of those situations, then we put an F for that situation. For all the other situations, we put in a T because we know the condition is going to be true in every other case. And we look, we've got one of those situations in the first row. So we've got a situation where A is true and not B is false, which means that we're going to end up with an F for the arrow there. And then we're going to put in a T for all of the other cases because the second row we've got TT, and that gets a T. We've got FF, that gets a T, FT, that gets a T. So it's the only case we're worried about when we're doing the conditionals. When you've got the first thing, you don't have the second thing, it's true in all the other cases. And we're going to cross these values off because we've computed those, we've used those to get that middle column, and we're done with them. All right, and that's the end. That's the completed truth table for this argument. Now, in order to work out whether the argument is valid or invalid, we do what we did with the previous argument, which is look for a row in which the premises are true and the conclusion's false. If there is a row in which the premises are true and the conclusion's false, then the argument is invalid. If there's no such row, then the argument is valid. And we're going to check row by row. So the first row, we've got the first premise being false. So the first row is not a row in which the premises are true and the conclusion false, so we can rule that out. Second row, first premise is true, second premise is false. So that's not a row in which the premises are true and the conclusion is false. Third row, we've got two true premises, but the conclusion is also true. So that's not a row in which the premises are true and the conclusion is false. And then the last row, the first premise is true, but the second premise is false. So that's not a row in which the premises are true and the conclusion is false. We've checked all the rows, and because we've checked all the rows and we haven't found any row in which the premises are true and the conclusion is false, we can conclude that the argument is valid. Right? It's impossible for the premises to be true and the conclusion false. And we can see that because we've written out all of the possibilities and we've checked them all one by one. So this is another valid argument. Okay, so that gives us two examples. Let's do one more example, and this time what we're going to do is we're going to focus on this detective case that we considered earlier on. So here we're going to have a little bit more complexity because in this case we've actually got three basic propositions to deal with. In the previous two cases we've only had two basic propositions to deal with, and so we've got to have to make a much more complicated, well, not a much more complicated truth table, but a truth table that is a bit more complicated than the truth tables we've looked at in order to assess this argument. First of all, we're going to start by translating the argument out into its logical form, which means finding the basic propositions, assigning them a propositional letter, and then working out the logical structure. So if we look at this, it looks like we've got three basic propositions. We've got the maid murdered Tom. That's the first proposition. The second proposition is that the butler murdered Tom. And then the third proposition is that the doctor murdered Tom. So we've got those three basic propositions. And here we've got either the maid, the butler, or the doctor murdered Tom. And what that is a double disjunction. So that's going to be the logical form of that first premise. The second premise, the maid didn't murder Tom. Well, we've said that the maid murdered Tom is A. This is the negation of A, so we're going to say not A for that second premise. And then for the third premise, the doctor didn't murder Tom, we're going to say not B because we've said, not C because we've said that C is that the doctor murdered Tom. So we're going to say not C there. And then the conclusion is that the butler murdered Tom. So we can conclude from this that B is true. Okay, and that's the logical structure of the argument. Either A or B or C, not A, not C, therefore not B. So what we're going to do now is we're going to put this into a truth table and we're going to test the argument to see if it's valid. All right, so let's start. We're going to draw up our matrix of possibilities. The matrix of possibilities here, because we've got three basic propositions, is going to have 8 lines. Remember, the number of lines in the truth table is 2 to the power of n, where n is the number of basic propositions. So because there's 3 basic propositions, that's 2 times 2 times 2, which is 8. Oops. Let's do that again. Doesn't like it when I draw there for some reason. Okay, so we've got our 3 basic propositions down, and now in order to get out all the possibilities, we're going to start with C, and we're going to go TF, 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 TF to get the 8 lines out for C, and then we're going to go TT, FF for B, and then A is going to be 4 T's and then 4 F's, and that'll get us out all the combinatorial possibilities. So T, F, T, F, T, F, T, F. Right, so there's 8 lines, and now we do B by going TF, TF, TTF, TTF, TTF. Sorry, TTFF, TTFF. Okay, that gets us the 8 possibilities for B, and then A is going to be 4 T's followed by 4 F's. All right, that gets us all of the combinatorial options out for these 3 basic propositions. And now what we've got to do is we've got to put our argument into the joint truth table for the 3 basic propositions. So we're going to put in our first premise, A or B or C. That was our first premise. Our second premise was not A. Our third premise was not C. And then our conclusion was B. Right, and now I put in the 3 dots for the conclusion, just to mark out that that's the conclusion of the argument. Now we're going to go one by one. Again, it's good to just start by doing the negations. We've got 2 negations here. We've got the negation of A and the negation of C, so we're going to do those first. So the negation of A, we just feed in the truth values for A and we reverse them to get the truth values for not A. So when A is true, not A is false, and so we're going to get 4 falses followed by 4 trues. And for not C, we're going to take in the values for C and we're going to reverse those, and so we're going to get a cycling between F's and T's. We're going to get FT, 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 FT because we're feeding in a T, getting out an F. All right, and now for B, we're just going to put in the values for B that we started with. That one's easy. So we're going to go T, T, F, F, T, T, F, F. All right. So we've got the conclusion, we've got 2 of our premises, we've just got to complete the last premise. Now in order to complete this last premise, what we have to do is we have to evaluate this double disjunction. Now when we're evaluating this complex proposition, we start with the thing that has the most brackets around it, and then we move out to the thing that has the least brackets around it. So if we look at this disjunction here, this A or B, that's got 2 sets of brackets around it. It's got this one set of brackets around the A or B, and then the second set of brackets around the A or B or C. So that's got 2 sets of brackets around it. We look at the or C, that's got 1 set of brackets around it, and that's it, because it's not inside the brackets with the A or the B. So the second disjunction, involving the C, has got 1 set of brackets around it. The first disjunction involving the A and the B has 2 sets of brackets around it, so we're going to start with the A or the B. Now remember the truth table for the disjunction. The disjunction is true when either A is true or B is true or both, and it's false when both sides are false. So what we're going to do is, because the false making situations are rarer, we're going to focus on finding those, we're going to mark those up, and then we're going to put in the true for the rest. So once we get the false situations down, we can just be confident that we can put in true for the rest. So we're looking at A or B, and we're looking for cases where they both fail. So if we read down these first 2 columns, we get to the second last column, second last row and the last row. What we see is that we've got 2 F's for A and 2 F's for B, so the disjunction is going to fail in those 2 cases. So we're going to put those 2 cases in first. And then we know that because those are the only 2 cases, that it's going to be true in every other situation. So we can just put 6 trues leading upwards. 1, 2, 3, 4, 5, 6, 7, 8, right? So that gets us our 8 lines. Now, what we have to do is we have to evaluate this disjunction with C. So what I'm going to do is I'm going to put C in, just in the same way that I put B in over here. So I'm going to start by putting that in. Ultimately, what I'm going to be doing is I'm evaluating this column for the A or the B against the column for the C in order to work out the disjunction of A or B or C. So let's put in C. That's just going to be true, false, true, false, true, false, true, false. And now for the disjunction, again, we're going to look for any situation in which both sides are false. And in this time, we're looking for situations in which the truth table for the A or B is false, or the truth table for the C is false. So let's look for those cases. If we look right down the bottom there, we've got a case where both sides are false. So we're going to put false in there. And we also can see that that's the only situation. It's true, either in all the other situations, either the left-hand side is true or the right-hand side is true. And because of that, we can put in true for the rest. And then we can get rid of these values. And now we've got the truth table worked out for that first premise, for that double disjunction. And that's the end of the truth table. Now, in order to work out whether or not the argument is valid in this case, we do exactly what we did in the 4-line truth table case. We look to see if there's any row in which the premises are true and the conclusion's false. If there is some row in which the premises are true and the conclusion's false, then the argument is invalid. If there's no such row, then the argument is valid. So let's go row by row. First row. First premise is true, second premise is false, so that first row is not a row in which the premises are true and the conclusion false. Second row, first premise true, second premise false, so it's not the second row. Third row, first premise is true, second premise is false, so it's not the third row. Fourth row, first premise is true, second premise is false, so it's not the fourth row. Fifth row, first premise is true, second premise is true, but the third premise is false, so it's not the fifth row. Sixth row, first premise is true, second premise is true, third premise is true, but the conclusion's also true, so that's not a row in which the premises are true and the conclusion's false. 7th row, first premise is true, second premise is true, third premise is false, so it's not that row. Last row, first premise is false, so it's not that row. So by looking at the argument row by row, we can see that there's no row in which the premises are true and the conclusion's false. And because there's no row in which the premises are true and the conclusion's false, we can conclude that the argument is in fact valid. Alright, so once again what we've got here is actually something at the level of a mathematical proof. We mapped out all of the possible situations, we tested each possible situation one by one, and we saw that none of those possible situations was one in which this argument could fail. And so, as a result, we conclude that the argument's valid. Doesn't mean that the argument is sound. The argument, for all we know, could be unsound because one of the premises could be false, but what we do know is that the argument is in fact valid. Okay, so all of the cases that I've looked at so far have been cases where you've got some argument and the argument turns out to be valid and we can prove that. And notice that the arguments that turned out to be valid are arguments that we intuitively thought were good arguments from the very beginning. Each of these arguments, if the moon is made of green cheese, then God exists. The moon is made of green cheese, so God exists. There does seem to be something good about that argument. It may not be sound. It may not be the case that the premises are true, but we nonetheless get the feeling that if the premises were true, we would be forced into the conclusion. Similarly, with this argument, if I'm cooking, then I'm not cleaning. I am cleaning, so I'm not cooking. There seems to be something good about this argument as well, something that sort of intuitively grabs us, which says, yeah, there's something right here, even if we don't know exactly whether the premises are true or not. And same with the detective argument. In each case, we've got something now that can back that up. We've actually got a proof that underpins our initial intuitions about whether or not those arguments seem to us to be true. But not all whether or not those arguments seem to be valid. But not all arguments are valid. Many arguments are invalid. And what we can also do is we can use the truth table method in order to demonstrate that an argument is invalid. And indeed, we can take it a step further. What we can do is actually produce a counterexample. And a counterexample to an argument, very roughly, is just a situation that makes the argument invalid. More carefully, what a counterexample is a row in the truth table, at least counterexamples in propositional logic. The counterexample in propositional logic is a row in the truth table in which the premises are true and the conclusion is false. And in order to draw out a counterexample, what we do is we isolate that row and we can pull out that row and say, look, here's a row where the argument is such that the premises are true and the conclusion is false, and because of that, there is a possible situation in which the premises are true and the conclusion is false. Now, in order to individuate that row, what we do is we focus on the values for the basic propositions that feed into the matrix on the left-hand side. So, for instance, if the row is one in which A is true and B is false, in the sort of the side of the matrix, then that's going to individuate our counterexample, and that's going to tell us the row in which the argument falls down. Now, it's important to note that there isn't always just one row that turns out to be a counterexample. You could have an argument where every row is a counterexample, and so there's no row in which it fails to be the case that the premises are true and the conclusion is false. Or you can have 2 rows, 3 rows, and so on. There could be any number of rows. It really depends on the particular argument that you're looking at. All you need, though, for an argument to be invalid is one row in which the premises are true and the conclusion is false, and that one row is sufficient to formulate a counterexample against the argument. Alright, so what we're going to do now is we're going to look at a couple of different arguments, and I'm going to take the argument in English, translate it into logic, situate it inside a truth table, and then actually prove to you that the argument is invalid, and from there draw out a counterexample so you can see how the entire process goes. Alright, so let's take this argument given to us by Daft Punk. We're going to see if the Daft Punk song Get Lucky is giving us a valid argument or not. So here's the argument. If I'm out for good fun, then I'm out to get lucky. Second premise, I'm out to get lucky. Conclusion, so I'm out for good fun. What we want to know is whether or not this is a valid argument. So first of all, what we've got to do is we've got to take each of the basic propositions in that argument, translate them out into propositional letters, map the logical structure of the argument, situate the whole thing inside a truth table, complete the truth table, and then read off the truth table to see if there are any rows in which the premises are true and the conclusion is false. Okay, so let's start with the translation step. So remember, what we're looking for are basic propositions, things that can be true or false, but that don't have any parts that can be true or false. So let's consider this first proposition. If I'm out for good fun, we're going to call that one A. Second proposition, I'm out to get lucky. We're going to call that proposition B. We've got that proposition B turning up as our second premise as well, and then our conclusion is A. And the logical structure of that first premise is a conditional. Okay. If I'm out for good fun, then I'm out to get lucky. I am out to get lucky, so it follows that I'm out for good fun. What we're going to do now is we're going to put this into a truth table, and we're going to test to see if it's a valid argument. All right, so 4 lines to our truth table, because we've just got A and B. TF, TF for B, and then TT, FF for A. And now we're going to put each of our premises into the truth table for this argument, and then our conclusion as well. So the first premise is if A, then B. Second premise is B, and then the conclusion is A. And we can mark up our conclusion again with our 3 red dots. All right, so what we're going to do is we're going to complete the truth table just like we completed the previous truth tables. We're going to be fairly quick about this one. We've got A and B, which we can just put straight in because we've already got those values over there. So we're just going to replicate those values over here. That gives us the possible situations under which the conclusion is true or false. And then we're going to put in our values for B to get the situations for the second premise. And now we're going to evaluate this first premise. This first premise is just the conditional, if A then B. And in order to evaluate that, we're just going to remember the truth table for the conditional. And remember, the truth table for the conditional tells us that the conditional is false in exactly one situation. And that situation is when you've got the first thing and you don't have the second thing. And if we look down the left-hand side of the matrix, we can see that there's one situation where we've got the first thing and we don't have the second thing. That's the second row. So we're going to put an F in for that. And then it's going to be T's for all of the rest. Okay, so now we've finished our truth table for our argument. We've translated the argument into our logical language. We've put it all into a truth table. We've completed the truth table. So what we've got here is now a proof. We've got to work out what the proof is a proof of. Is it a proof that the argument is valid, or is it a proof that the argument is invalid? In order to work this out, we're going to have to go row by row. What we're looking for, again, is a row in which the premises are true and the conclusion's false. If there is such a row, then the argument's invalid. If there's no such row, then the argument's valid. So let's start with the first row. First row, first premise is true. Second premise is true, but the conclusion's true as well. So that's not a row in which the premises are true and the conclusion's false. Second row, first premise is false. That's not a row in which both the premises are true and the conclusion's false. Third row, first premise is true, second premise is true, and the conclusion is false. So what that means is that that third row is, in fact, showing us that this argument is invalid, right? Because there is a possible situation under which the premises are true and the conclusion's false. So first of all, we can write down that the argument is invalid, so we now know that. So Daft Punk did, in fact, give us an invalid argument. And now what we have to do is work out the counterexample. And the counterexample is given, the information for the counterexample rests in the side of the matrix over here. What we're looking for is the possible situation, the values for A and B, under which the premises of the argument are going to be true and the conclusion's false. And what we can see is that when A is true, A is false. Hang on, let me just get rid of that. When A is false, and B is true, because that individuates this row, this third row, and it uniquely individuates that row because no other row has those values, then that's the situation under which the premises are true and the conclusion is false. So the argument's invalid, and that's a counterexample. If we translate that back out into English, we now have we can give an English statement of the counterexample. So remember what A and B represent. A represents that, well, if we go back to here, get rid of that. If we go back to our actual argument from Daft Punk, remember that A was I'm out for good fun and B is I'm out to get lucky. The counterexample, which was the case in which A equals F and B equals T, where A is I'm out for good fun and B is I'm out to get lucky. The sort of common sense counterexample here is that this argument is going to fall over when I am not out for good fun, but I get lucky anyway, right? So the situation is when you get lucky, but you turn out to not be out for good fun, which sort of makes sense, right? From the fact that you're out to get lucky, it turns out not to follow that you're out for good fun, because it could be the case that you get lucky without having any fun, which is a poor night indeed. All right, let's do another one. Next case. Again, what we're trying to do is we're trying to work out whether this is a valid or invalid argument. This time the argument's given to us by Taylor Swift. If I've got a blank space, then I'll write your name. I don't have a blank space, so I won't write your name. That's the argument we're given. So we're going to work out whether this argument is valid or invalid. First of all, we've got to work out what the basic propositions are. Then we've got to map the logical structure, situate the whole thing inside a truth table, and then do the proof. So let's start by mapping the basic propositions. I've got a blank space, so let's call that proposition A. We've got I'll write your name. Let's call that proposition B. I don't have a blank space, so that's the negation of A. And then the conclusion is, so I won't write your name, and that's the negation of B. So that's the structure of the argument for the premises, the second premise and the conclusion. Now we've just got to work out the logical structure of that first premise. Because we've got this if-then situation, we know that this is going to be A conditional. Okay, so that's the structure of our argument. If A, then B. Not A, therefore not B. Is it a valid argument? Let's find out. So again, we start by setting up our matrix. A, B, and we go TF, TF for our Bs, and then TT, F, F for our A's, and that gets us the basic setup. And now we're going to put our argument inside the truth table. So we got A, arrow, B. That was our first premise. Our second premise was not A, and then our conclusion was not B. All right. Now we've got to evaluate each of these propositions. Let's start with the negations because they're easy, and then we'll do the arrow, and that should get us to the finish. So let's start with B. Remember, to do the negation for B, you just take in the values for the basic propositions over here, you reverse them in order to get the not B. So we're going to take in a T, and we're going to spit out an F, take in an F, spit out a T, in order to get all of the values for not B. And then we're going to do exactly the same thing for not A. We're going to bring in our T's, spit out F's, bring in F's, spit out T's, in order to get those values. So that gets us our 4 rows for not A and not B, and then we've just got to do this conditional. The conditional, again, it's only false when you've got the first thing and you don't have the second thing. We look for that situation. We've got one in the second line, so it's going to be false there and true in all the other situations, because that's the only case in which you've got the first thing and you don't have the second thing. So now we've got our completed truth table for the argument, and we want to know, is the argument valid or invalid? So again, we've got a proof in front of us. We've just got to now interpret the proof. We've got to try and work out what the proof is actually telling us about the argument. We go row by row in order to look for a row in which the premises are true and the conclusion's false. If there is such a row, then it's invalid. If there's no such row, then the argument is valid. So let's start with the first row. In the first row, the first premise is true, but the second premise is false. So that first row is not a row in which the premises are true and the conclusion's false. The second row, the premises are both false, so that's not a row in which the premises are true and the conclusion's false. In the third row, the first premise is true, the second premise is true, and the conclusion is false. So the third row is in fact a row in which the premises are true and the conclusion is false. So what do we know? Well, we now will know what this proof is telling us. This proof is telling us that the argument is invalid, and we can draw out a counterexample. Once again, the counterexample is individuated by this information over here. So we're always looking to this side of the matrix when we're doing truth tables in order to work out the information for the counterexample. It turns out that the counterexample here is actually structurally the same kind of counterexample that we had for the previous argument. In this situation, when A is false and B is true, then the argument, that's what demonstrates that the argument is invalid. So we've got an invalid argument, and this is the counterexample here. The situation when A is false and B is true, namely which individuates that third row exactly, that's the case in which the argument falls down. So if we now come back to the English argument, if I've got a blank space, then I'll write your name. I don't have a blank space, so I won't write your name. And we're just going to add our counterexample in when A is false and B is true, right? So we know that this argument is invalid. We know that Taylor Swift gave us an invalid argument, and because she gave us an invalid argument, we can draw out the counterexample that demonstrates that the argument is invalid. And the argument is invalid when A is false, so when you don't have a blank space, and when B is true, when I write your name anyway, right? So the situation in which you don't have a blank space, but in this case in which Taylor Swift doesn't have a blank space, but she writes your name anyway, that's the situation in which the argument is going to turn out to be invalid. And again, you can kind of see that intuitively if you look at the argument. The argument is moving from having a blank space to writing your name. That you don't have a blank space, it doesn't follow from that she won't write your name, because she could write your name even though she doesn't have a blank space, at least insofar as the information that we've got in the argument would lead us to believe. Okay, so the truth table method, at least for propositional logic, is in fact the foolproof method that we've been seeking. What it allows us to do is determine with mathematical precision whether or not an argument is valid or invalid. But we have to be very careful not to draw too much out of the truth table proof system. So let's just have a rundown of the sorts of things you can and can't do with truth tables. So what can we do with truth tables? Well, we can use it to work out whether or not, we can sort of use it to classify the nature of a single proposition. So we can use it to work out whether a proposition is a tautology or a contradiction or satisfiable and so on. We can also use it to work out the relationship between two propositions. So we can use it to work out whether two propositions are jointly satisfiable or equivalent or contradictories or contraries or whatever. And now we can also use it to work out whether or not an argument is valid or invalid, and when the argument is invalid, to draw out a counterexample from the argument. What can't you do? Well, one of the things that is very difficult to do, there are certain special situations under which what I'm about to say won't hold, but for the most part what I'm saying is true. It's very difficult to say a great deal about soundness when you're looking at these truth tables. So if we look at these truth tables are a map of all of the possibilities, and one of those possibilities is going to be the actual possibility. It's going to be the world that we live in with the values for these propositions set as they actually are. The trouble is that from the truth table information alone, we can't work out which one of those rows represents the actual world and thus represents the situation that we live in. In order to work out whether or not an argument is sound, however, we need to not just know whether the argument is valid, we also need that further information about whether or not the premises are true. Which is to say, we need to know which of those rows in the truth table represents the actual world. But the truth table, for the most part, isn't going to give you that information. There are some very special cases where the truth table might give you that information. For instance, if every row in the truth table for the premises is a row in which the premises are true, so if you have two sort of premises and they're both tautologies, then every row is going to be one that's true. From that, you might be able to determine whether or not the premises are true, because although we don't know which one of those rows is the actual world, it doesn't really matter because the same information holds at every possible situation. But that's really a special case and one that you won't see very often. For the most part, you can't actually work out whether or not an argument is sound just by staring at a truth table. But you can, to some extent, work out whether an argument is unsound. Remember that soundness, for an argument to be sound, requires that an argument is valid and for the premises to be true. So when you do a demonstration in a truth table that demonstrates that an argument is invalid, you're also demonstrating that an argument is unsound because validity is required for the argument to be sound. So if you show that there's no validity, then you lose soundness as well. So although you can't show that an argument is sound, right, you can't demonstrate that the premises are in fact true because we don't know which row of the truth table we fall in, you can work out whether or not an argument is unsound when it is, because you'll see that at least with respect to validity, because you'll see that the argument turns out to be invalid when the argument is unsound and you put it inside a truth table. That said, if your argument is valid and you put it inside a truth table, it could be sound or it could be unsound. You're not going to get that information out straight away, except in some special cases. For the most part, you're going to have to take a further step to work out whether or not the premises are in fact true in that situation. But if the argument's invalid, then that's going to directly tell you that the argument is unsound. So, in short, you can work out unsoundness in some cases, but it's very hard to work out soundness except in some very, very special cases where you're dealing mostly with tautologies. All right, that's the end of today's session. Just to recap what we've done is we've taken the basic truth table method where we were situating joint propositions inside a truth table, and instead of situating just joint propositions and classifying them, we've taken entire arguments and situated them within a single truth table in order to be able to say something about whether or not the argument is valid or invalid. And what we did is we drew out a method for working out whether or not an argument is valid and whether or not an argument is invalid, and we also saw that when an argument is invalid, we've got a way to pull out a counterexample in order to demonstrate the situation under which the premises for that argument are true and the conclusion is false. What we're going to do in the next session is abstract away a little bit from the specific results that we got here in order to prove something a little bit more general about arguments and about propositional logic, which will enable us to come up with a sort of quick and dirty way of classifying arguments as we see them based on some general proved results that we can draw out of the truth table system. Until then, I hope you enjoy working on your truth tables in your practice time and when you're working with your tutors inside your tutorials. Thanks.